So some molecules have more than one valid Lewis structure. I mean, we just saw that with the H2CO. We drew two structures, and they both satisfied the octet rule. And how do we choose? But we have other things that are even stranger, like ozone. So ozone is 3 oxygens. And so they're going to have to be in a line because there's no other way you can do that. Each oxygen has 6 valence electrons, right? So 3 times 6 is 18. But 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm short 2 electrons. So I need to make a multiple bond, right? So this guy needs more. I'm going to take a lone pair from this one because he's got enough to share. I'm going to move that over here and make it a bonding pair. 2, 4, 6, 8, 10, 12, 14, 16, 18. Still the right number of electrons. So here we have oxygen in the middle, an oxygen on each side. One has a single bond, the other has a double bond. Why does this oxygen have the double bond? Why not that one? There's no good reason. We could draw it the other way. Oops. Let's be a little more careful here and try to put them in the same positions, just to avoid that being a confusing factor. So these might look like the same thing, but this oxygen is not the same as that oxygen. It's a different oxygen. Think of these as twins, right? Twins are not really interchangeable. They may look exactly the same, have the same DNA, but they're going to say, hey, no, I am different. I'm Susan, and that's Shirley, or whatever. I don't know where that came from. So these are 2 different oxygen atoms. Why does one oxygen atom here get the double bond, the other not? How do we choose one or the other? Well, the truth is, in nature, we don't choose. It isn't chosen. There actually is no difference between them. The actual ozone molecule exists as a sort of average of those 2. The ozone molecule does not have a double bond and a single bond. The bonds between the oxygens on both sides are the same. Lewis theory cannot do that, can't represent that. And so the best we can do in Lewis theory is to draw both possibilities and put a double-headed arrow between them. And we call this resonance, which gives us sort of a mistaken image of this, that it's resonating between, that the bonds are going back and forth. That's not actually what's happening. These are called resonance structures. So that's how we represent it in the Lewis model, but the actual structure is more like this guy right here. Come here. It's really tiny, isn't it? Let me make that bigger. So we've got a 1.5 bond on each side. It's equal. They're sharing. Lewis structures can't represent that, and so we've got this one or that one. The real thing is this hybrid. So here's a picture of dogs. So we got a German Shepherd. And what do you think that one is? A white lab or a golden retriever? Golden retriever. We'll say this is a golden retriever. So we've got German Shepherd and a golden retriever, mom and dad, and they have puppies, and the puppies might come out like this. This puppy looks the same all the time. It doesn't sometimes look like a German Shepherd and other times look like a golden retriever, right? It looks like a combination of the 2 parents. And that's what this resonance hybrid is. It's a combination. We represent it in Lewis theory by drawing the two different possibilities, but we recognize that it's actually a combination. So this is like my husband, and this is kind of like me, right? We have 6 children, so that would equate to a triple bond, right? Triple bond. If you look at my kids, they don't look exactly like my husband, and they don't look very much like me. They do all look like each other. It's like cookie cutter children. But they're a hybrid. They're a combination of the two of us. My husband's Japanese. I'm Swedish, of Swedish ancestry for the YouTube people. So you can imagine the half Viking, half samurai. It's a good, vigorous mix. Combination, okay? So the resonance hybrid is not going back and forth. The reason Lewis theory has a problem with this is that the electrons are localized in the Lewis model. We have to say electrons are here or here. They have to be either on an atom as non-bonding pairs or between 2 atoms. And actually, what happens is the electrons can be delocalized and shared over the entire molecule. And we'll talk about a different bonding theory that uses that concept. So when those electrons are delocalized over several atoms or bonds, we get a lowered energy, lower potential energy, and that is called resonance stabilization. It's also an important concept in Octet. Okay, so write a Lewis structure for the NO2 ion, the nitrite ion, include resonance structures. Well, we've got 2 oxygens and a nitrogen, and we have to figure out how to put them together. There isn't any hydrogen to stick on the outside. Another guideline is that more electronegative elements are typically on the outside. What's more electronegative, nitrogen or oxygen? Who's closer to fluorine? Oxygen. So let's put the nitrogen in the middle and put the oxygens on each side. We have to count up valence electrons. We've got a nitrogen with 5 valence electrons. We have 2 oxygens. They each have 6. And a -1 charge means we add an extra electron. So we've got 18, right? So we've got 2, 4 for the bonds. 6, 8, 10, 12, 14, 16, 18. It's not a coincidence that this ends up looking like ozone. Ozone also had 18 electrons and 3 atoms. So we don't have enough. So nitrogen has an octet, this oxygen has an octet. We're going to take one of these lone pairs and share it with this deficient oxygen. Now everyone has an octet. It's an ion, so we're going to put brackets around it and put the charge on the outside. So that's a Lewis structure for nitrite. When you see a situation like this, I have 2 oxygens. One has a double bond with the nitrogen, one has a single bond with the nitrogen. Why does this oxygen get the double bond? Why not that one? There's resonance, okay? For the most part, resonance is being able to move a multiple bond so that it's between the same 2 elements but different atoms. So this was between nitrogen and oxygen. I can also have that double bond between nitrogen and oxygen over here. So those are the resonance structures. So nitrogen with oxygen on each side, but I'm just going to draw the mirror image of it. I'm going to put the double bond over here. And so that one has 2 pairs of non-bonding electrons. The nitrogen still has its lone pair, and this oxygen has 3. Still an ion with a negative charge, and a double-headed arrow saying resonance. The actual ion is between those. It's a hybrid, and it's a 1.5 bond, but the Lewis model can't deal with that. Any questions? So I showed you how you can kind of predict the number of bonds that a given atom is going to form. A more rigorous way to determine that is called formal charge. So the formal charge for an atom in a Lewis structure is the charge it would have if all of the bonding electrons were shared equally between those bonded atoms. So we're going to totally discount any bond polarity or anything. Formal charges are fake. These are fictitious charges. They're something we make up to help us figure stuff out. We're ignoring electronegativity. So the formal charge is going to be the difference between the number of valence electrons that that atom has by itself and the number of electrons that it owns in a Lewis structure. So if you like equations, the formal charge is equal to the number of valence electrons minus the quantity, the number of non-bonding or lone pairs, plus half the bonding electrons. So if you like that, you're fine. And if you don't like that, I'm going to show you a different way. Of course, we have to have rules. The sum of all the formal charges basically has to add up to the charge on the molecule or the ion. If it's a neutral molecule, they have to add up to 0. If it's an ion, the formal charges add up to the charge in the ion. Small or 0 formal charges are better. So looking at formal charges is going to help us choose between different Lewis structures that satisfy the octet rule, but obviously they can't all be correct. If you can't avoid formal charges, and with an ion, there has to be a formal charge somewhere, but sometimes neutral molecules also have formal charges, then you're going to put the negative formal charge on the more electronegative atom, because that's the one that's like attracting electrons anyway. So, HCN, hydrogen cyanide or hydrocyanic acid if it's dissolved in water. So they've got the structures up here, but I'm going to write them down here as well so that I can cut them apart. So one of them puts carbon in the middle and nitrogen on the end, with the nitrogen having a triple bond. And the other one puts nitrogen in the middle and the carbon on the end. So formal charges can help us identify which one of these is better. We can also use what I was talking about earlier, looking at the number of bonds is going to probably be equal to the number of unpaired electrons. So if I look at carbon, 4 valence electrons. How many bonds? 4. Nitrogen, 5 valence electrons. How many bonds? 3. If carbon has 4 bonds, it's going to have a 0 formal charge. If nitrogen has 3 bonds, it's going to have a 0 formal charge. So looking out for that can help you start off with the structure that's more likely to be correct. Just looking at that, which of these is better? Carbon here has 1, 2, 3, 4 bonds. Nitrogen has 3 bonds. That's what they would like. Over here, nitrogen has 4 bonds. Carbon has 3 bonds. There will be formal charges there. So let's see how the formal charge thing works. I don't like the equation business. So what I'm going to do is I'm going to think of this molecule as some sort of a small corporation. Some 3 people came together, they pooled their resources, they made a business, and now they've decided to stop. They're not going to be together anymore. They're just going to cut everything that's shared equally and go their separate ways. I used to talk about them getting a divorce, but there's 3, so that doesn't work very well. So what I'm going to do is I am going to cut the bonds in half. Remember that on each side of this bond, these bonds, is an electron. Okay? So we're cutting it up, we're breaking up the business, they're going their separate ways. The formal charge is the difference between what that atom brought into the business and what it's leaving with. So what it brought in is the number of valence electrons. So hydrogen has one valence electron. It brings in one valence electron. When it leaves, how many electrons is it getting? One. It's coming out even. It's breaking even. So this has a formal charge of 0. Carbon had 4 electrons, valence electrons, when it came into this business, and now when we're splitting up all these bonds, it's leaving with 1, 2, 3, 4. It also broke even. Nitrogen brought 5 valence electrons, and when it leaves, 1, 2, 3, 4, 5. 0, 0, 0. That's good. That's probably the right one. Let's look at this one. Again, we're going to cut up the bonds. Just cut them in half. Hydrogen had 1 valence electron when it came in, and it's leaving with how many? 1. So 0 formal charge. Nitrogen brought in 5 electrons, and how many is it going to leave with here? 4. 5 minus 4 is 1. So that's a +1. Carbon brought 4 electrons in, and now it's leaving with 5. 4 minus 5, minus 1. So the carbon has a -1 formal charge. It's got an extra electron if we broke up the bonds. Nitrogen has a +1 charge. It's kind of missing an electron. So this is not as good. So given these two, we choose this one. This one's probably going to be more stable, and this is the correct structure. Any questions? Assign formal charges to each atom in the 3 resonance forms of N2O. Nitrogen is central. Okay, that's not something that would be obvious, so we're telling you. Put nitrogen in the middle. Which resonance form is likely to contribute most to the correct structure of N2O? Okay, so we've got nitrogen in the middle, and a nitrogen on one side, and an oxygen on the other side. Each nitrogen has 5 valence electrons, so we've got 2 times 5, and oxygen has 6. So that's 16 electrons to mess around with here. We've got 2, 4, 6, 8, 10, 12, 14, 16. I don't have enough. Need to do some sharing. Well, as I just kind of randomly made this, the nitrogen in the middle has the octet, so we're going to take one of its lone pairs and share. Let's share with this nitrogen. This nitrogen doesn't have enough. So nitrogen in the middle shared a lone pair with this nitrogen now. This nitrogen has 8 valence electrons, and this one also has 8 valence electrons. The oxygen is still deficient. It only has 6. So this oxygen's bonded to this nitrogen, and so we're going to take that lone pair and share it with the oxygen. Okay? Well, how else could we put that together? Like, well, we can't just move a double bond, right? What if we did, we need 4 bonds, basically. What if we did a triple bond and a single bond? So let's try a triple bond over there and a single bond on this side. Same number of bonds as over here, so same number of lone pairs. So I can put 1 lone pair on that nitrogen, and I've got enough lone pairs to give that guy an octet. You can count them up, it's the same number of electrons. Or we could put the triple bond with the oxygen. Oops, not there. All 3 of these structures obey the octet rule. These are resonance structures. They differ only in the placement of multiple bonds. The atoms are connected in the same way. Do any of these have all zero formal charges? No. For everything to have zero formal charge, each of the nitrogens would have 3 bonds, the oxygen would have 2 bonds. And none of them are like that. So we've got formal charges going on here. Let's see what they are. So cut those bonds in half. Nitrogen brings in 5 electrons, it leaves with 6. -1 formal charge. Nitrogen brings in 5 electrons, this one leaves with 4. 5 minus 4 is +1. Oxygen brings in 6, leaves with 2, 4, 6, 0. See how I did that? Isn't that better than that silly equation? Half the bonding pairs. Well, just cut them up and count the dots. Good grief. Okay, so nitrogen brings in 5, because 5 valence electrons as an individual atom. Here it's leaving with 2, 3, 4, 5. 5 minus 5 is 0. This nitrogen also came in with 5, leaving with 4, +1 formal charge. Oxygen brings 6. This oxygen's leaving with 7, -1. Notice that these formal charges add up to the charge on the molecule. +1, -1 adds up to 0. This adds up to 0 also. It's just that they're in different places. I'll do this one over here. Nitrogen brings 5. Here it's leaving with 7. 5 minus 7 is -2. Nitrogen comes in with 5, leaves with 4, +1. Oxygen comes in with 6, leaves with 2, 4, 5, 6, 7. Yeah, -1. No, +1. Sorry. Okay, major brain fart. Comes. It's not supposed to be this hard. Oxygen comes in with 6 and leaves with 7. So that's -1, right? But it's not adding up. What?
The very last one, I think we gave oxygen an extra lone pair.
Yes, thank you. I had too many dots. That's why it's not working out. Yeah. There we go. I'm like, it's not adding up. It's not adding up. So that's +1. So adding up the formal charges, if they don't add up, that can point out problems like that. So we're going to pick the one that contributes the most likely one, based on the one that has the lowest formal charges. So here we've got 2, 1, and 1. Here we've got 0, 1, and 1. Here we've got 0, 1, and 1. So these both have the lowest formal charge, right? So we'll rule that one out because it's got higher formal charges. Not that it can't happen, but it's not going to be significant. Now we have to choose between these two. The other rule was if you have a negative formal charge, give it to the more electronegative element. So oxygen is more electronegative. Oxygen is going to be more comfortable having a negative formal charge. And so this is also not the best one. This is the best one. So this has the best arrangement of formal charges. These others will exist to a small extent, but this is going to be the major contributor to the structure of this molecule. Any questions? Draw the Lewis structure, including resonance structures for diazomethane, CH2N2. Carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charges. A lot of times when there's a 0 formal charge, we don't bother writing the 0. We just write them if there are formal charges. So we start with trying to figure out how we're going to connect this. It says that carbon is central. So let's try putting the hydrogens and the nitrogens on that carbon. That's carbon being central, right? And we're going to count up electrons. Carbon has 4 valence electrons, 2 hydrogens, they each have 1, 2 nitrogens, they each have 5. Don't be embarrassed to get your calculator out and do this, because if you do the math in your head and you get the wrong number of electrons, it's going to mess everything up. 4 plus 2 is 6, 16. Go ahead and check me if you want. Yeah, good. Okay. It's a peanut gallery over there. So I've got 2, 4, 6, 8, 10, 12, 14, 16. Ran out pretty fast there. Everybody happy? No. Carbon and hydrogen are happy. The nitrogens aren't happy. We don't have enough electrons. We should share more. We should make multiple bonds. Carbon doesn't have any lone pairs to share. If I take a pair from the nitrogen and stick it in here, then carbon's going to have too many, and nitrogen's still going to have the same amount. This just doesn't work at all, does it? So we must have connected it wrong. Well, what can we do? We can't put anything on the hydrogens. It said carbon is central. What if we move this hydrogen to one of the nitrogens? That'd be okay. So let's do that. We'll put the hydrogen over here. Ooh, well that helped out that nitrogen, didn't it? Now this nitrogen has 2, 4, 6, 8. Well, the carbon only has 6, so we could take this lone pair here and share with the carbon. And now this carbon and this nitrogen have 8. But what about this nitrogen? We can't do another double bond with carbon. So again, we must not have things connected correctly. So we can take this hydrogen and put it on the nitrogen. So it's like all crooked and bent up, but that's okay. So now this nitrogen can share another pair with the carbon. And now we've got octets for everybody. And we say, well, is carbon central? Now carbon's in the middle, we just interpreted it wrong. So I'm going to move this part down here because that just kind of bothers me. So I'm just going to swing that up and make this straight. Double bond, nitrogen, lone pair, hydrogen. Okay? Nitrogen likes to have 3 bonds, right? How many bonds does nitrogen have? 3. Carbon likes to have 4 bonds. It's got 4 bonds. Nitrogen likes to have 3 bonds. It's got 3 bonds. This has all 0 formal charges. Let's prove it to ourselves. Cut it up. Nitrogen brings in 5 electrons, leaves with 5. That one's 0. I'm not going to write anything. Carbon comes in with 4, leaves with 4. Nitrogen comes in with 5, leaves with 5. Hydrogen's always 0. No formal charges on that one. So it says there's resonance structures. This is like a previous one. We had 2 double bonds. We could move one of these over here. We could make one triple bond and one single bond, right? So hydrogen, nitrogen, let's do a triple bond there and a single bond. Or we could put it on the other side. Right? I'm just playing around with where the multiple bonds are. And so then this structure has 2 lone pairs in it, so I can put 2 lone pairs in here. They're going to go on this nitrogen and on this nitrogen. Do these structures have 0 formal charges? Carbon has 4 bonds. Do the nitrogens each have 3 bonds? No, they don't. There will be formal charges. Let's figure out what they are. Cut the bonds in half. Nitrogen brings in 5 electrons, leaves with 4. 1, 2, 3, 4. 5 minus 4 plus 1. Carbon brings 4 in. How many is it leaving with? 4. That's 0. I'm not going to write it. This nitrogen brought 5, and he's leaving with 6. 5 minus 1. No. 5 minus 6 is minus 1. This one, we don't really have to do all that again. This nitrogen with the triple bond and the single bond is in the same situation as that. It's going to be plus 1. This nitrogen and that nitrogen have the same situation. This will be negative 1. So these are resonance structures. So which one probably contributes the most to the resonance hybrid? The one with 0 formal charges. Any questions?